is a PowerPoint that I made when the school was having a day to discuss energy. The vice president, the old vice president, used to have an interesting topic that was discussed at the end of the year. And the topic was energy. So I thought we were going to have a whole bunch of non scientists in there talking about energy. And I thought there should be at least one talk that was about real energy. So I wrote this for a general audience, and I called it A Child's Introduction to the Laws of Thermodynamics. And here it is. Child's Introduction to the Laws of Thermodynamics. Now, I'm only giving you the first 10 or 11 slides of this because I'm just introducing you to the beginning of our study of thermodynamics. Energy. So any talk about thermodynamics starts with energy. And any talk about energy starts with internal energy. So what is internal energy? Well, it's the sum of the kinetic energy of the moving molecules. So if you have an atom, it's just simply translational kinetic energy. But if you have a diatomic, then you have translational kinetic energy, but you also have rotation and you also have vibration. So there's different kinds of kinetic energy. And actually, vibration also has a contribution from potential energy. Is there anything else? Well, yes, pretty much everything to us chemists. And what there is there's bonds. And while I have a big boom there, I am trying to illustrate that it takes energy to break a bond, not that it releases, because it doesn't. It requires energy to break a bond. Breaking bond requires an input of energy, and this, to break a typical bond, requires a much larger input of energy than all of those kinetic energy contributions I talked about. So if you were to sum up all of those contributions from, rotation, vibration, and all that stuff, you would get something that I would call very small potatoes on the energy scale. Not a lot of energy. But when we're talking about the energy that goes in to break a bond, so that's an uphill process, and the energy that goes out in the downhill process of making a bond, then if you put all that together, that's very large potatoes. Okay, that's a really big deal. So bonding is really important. And here's just an illustration. If you have two separated hydrogen atoms, and we have a scale, let's say, of internal energy on the y-axis, that H2 is lower in energy than two H's, and O2 is even more lower in energy than two O's. That's really mainly because oxygens have bigger positive nuclei that attract those electrons involved in the bond more strongly. So if I were to draw the internal energy on the y-axis and put those separated, say 2 separated O atoms and 4 separated H atoms, that would be a certain value on that scale. And if then I made 2 hydrogen molecules and 1 oxygen molecule, that would be a lower energy because you have to make bonds to go from the top to the bottom. And it's a downhill process when you're making bonds. Energy is released. So the next sort of obvious question is, well, what else can you do with hydrogen atoms and oxygen atoms? And of course, what you can do is make water. All right, now, so where does water fit on this scale? So if that's the hydrogen atoms up there and the hydrogen molecules and oxygen molecules, water is lower in energy. Okay, so it's the lowest of those three. And the difference in internal energy between the hydrogen molecules and oxygen molecules and the water molecules is the delta U that I'm showing you here. So what should happen when hydrogen molecules and oxygen molecules react to form water? Well, what these videos show that I'm not going to do with you now, you can do them at home if you like. I'll give you this PowerPoint to play with. Well, you'll get a giant explosion if you ignite an H2 molecule. Just give it a tiny bit of activation energy and it's completely downhill. So you get this big boom, and so where did the energy go? So is that energy lost? And according to the first law of thermodynamics, it's not lost because energy has to be conserved. So there are only two places it can go. It can go into work or heat. But I have to stop here because we really can't get into bonding yet. We have to do some fundamental work. And that's what I'm going to do next. Just tell you about that fundamental work.